Boundaries between worlds blur more than you think, and the shadow universe brushes our reality in quiet, meaningful ways. In this video, we map what a hypothetical world that intersects ours would actually look like, from subtle glitches in technology to echoes across time and memory. You'll see why this isn't just sci-fi. It reframes history, physics, and what we call real. If you crave mind-bending ideas that stay grounded in curiosity and evidence, you're in the right place. Let's dive in. Conceptual foundations. The shadow universe rests on a two-layer ontology in which a real but largely unseen realm intersects ours, sharing a substrate of physical law while hosting configurations that rarely appear in ordinary observation. That boundary is neither fixed nor simple. A practical way to frame it is to imagine a shared scaffold, space, energy, and information, that carries elements from both worlds, with the shadow layer capable of manifesting partial states that map to, but do not equal, those in our reality. Not all events cross. Cross-border mappings are structured by invariants and symmetries so that if a state exists in one world, its shadow analog is constrained by the same global rules, preventing endless chaos at the boundary. This keeps explanations testable. For example, a shared energy field would allow faint correlations between creatures or objects near a boundary, producing simultaneous, albeit muted, phenomena such as a glow in a window frame that can be seen from either side. Boundaries are dynamic. They bend with energy flows, and sometimes consciousness can influence their permeability by focusing attention or intent. Limits exist. A lamp in our world might cast a softer, version glow into the shadow world, while a shadow event, like a traffic ripple, could produce mirroring patterns in our environment that we interpret as anomalies. These effects are not miracles. They are predictable edge cases where the mapping weakens and the interaction rules allow leakage of information, energy, or form without enabling direct signaling. That keeps communication subtle. Consider a painting visible across both realms, its colors shifting differently as boundary conditions shift. Observers describe divergent interpretations, yet the underlying state remains connected through shared structure. The conceptual foundations also demand a robust logic for identity and change across domains. Two guiding principles emerge. First is correspondence. There must be a principled mapping from events and objects in our world to their shadow counterparts, with a clutch of allowable transformations that preserve core properties such as continuity, causality, and energy balance. Second is coherence. The boundary rules must prevent paradoxes, so unexpected loopings or faster-than-light signaling cannot arise. This is ensured by constraints reminiscent of no signaling in quantum theory, adapted to cross-world interaction. Evidence accrues via cross-world anomalies that align with the mapping. A concrete example would be a resonance pattern that appears at a specific location and time in both worlds, yet with a phase difference that maps to a change in boundary permeability. Repeated observations would reinforce the mapping's validity and help distinguish genuine cross-world effects from artifacts. From a practical stance, these foundations guide how we talk about the shadow universe. Researchers build models that are explicit about what counts as evidence, what remains conjectural, and how to falsify competing frameworks when new cross-world signals emerge. They prioritize internal consistency. Ethical and design considerations follow, asking who can influence the boundary, what safeguards prevent harmful leakage, and how societies adapt to technologies that tap into shared substrates without destroying the separation that keeps each world intelligible. Story worlds gain texture when these foundations are treated as living constraints rather than mere background lore. In practice, a practitioner might propose a taxonomy of boundary phenomena, permeabilities, coupling constants, and observables, that helps compare hypotheses and guide speculative but disciplined research. Evidence, models, and predictions. Evidence for a shadow universe would hinge on observations that resist conventional explanations and on anomalies that standard physics cannot fully account for. Several investigative threads keep returning to the possibility that hidden sectors or intersecting brains could couple to our world in subtle ways. In astrophysics, unusual energy budgets, unexpected cooling rates in dense objects, or subtle imbalances in gravitational dynamics can raise questions about unseen channels through which energy and momentum might travel. In laboratory settings, tests of gravity at very short distances aim to reveal deviations from the inverse square law that could signal extra dimensions or new forces. Particle physics experiments search for portal interactions and hidden sector particles that could bridge our world with a shadow counterpart through Higgs, vector, or neutrino portals. Collectively, these avenues form a lattice of evidence that stays speculative until a coherent pattern emerges. Models that frame the shadow universe in concrete terms range from brain-world scenarios with extra dimensions to mirror matter and hidden sector frameworks with specific portal couplings. In brain-world pictures, gravity or other fields might seep into neighboring dimensions, altering how forces propagate on small scales or in high-energy environments. Hidden sector theories posit a parallel set of particles that barely interact with familiar matter, but can exchange energy or momentum through select portals. The many-worlds approach provides a philosophical scaffold for considering branching realities that could intersect under particular conditions, though it remains interpretive rather than predictive in a direct experimental sense. Mirror matter models propose a copy of ordinary particles living in a parallel sector, offering mechanisms for dark matter phenomenology that resemble familiar physics but with distinct interaction patterns. Each family of models yields distinct experimental signatures that researchers actively map against existing data. Predictions surface in several practical, testable forms. Some scenarios anticipate small but detectable departures from Newtonian gravity at very short distances, constrained by precision experiments that push toward tighter limits on new forces or dimensions. Other models imply that gravitational waves or high-energy signals could exhibit subtle energy leakage, damping, or echoes if portals to a shadow sector become transiently accessible during extreme events. Neutrino and collider experiments are expected to constrain or reveal sterile or hidden sector particles that couple weakly to standard matter, altering production rates or decay channels in measurable ways. In astrophysical observations, anomalous cooling rates, unexpected energy loss in compact objects, or correlated footprints across different messengers could point to hidden channels transferring energy to a shadow sector. Importantly, these predictions remain contingent on the specifics of a chosen model, and no single line of evidence has achieved consensus as proof of a shadow universe. As a practical guide for interpretation, researchers emphasize cross-validation across independent observables and multi-messenger signals. The strongest cases arise when a single hypothesis simultaneously explains several anomalies without overfitting any one dataset. For instance, if a specific portal mechanism predicts both a slight gravity deviation at small scales and a corresponding signature in particle production rates, consistent findings across experiments would bolster the case. Conversely, the absence of consistent signals tightens the constraints on model parameters and narrows the viable landscape of scenarios. In short, the evidence, the array of models, and the spectrum of predictions form a triad that researchers continuously refine as new data arrive and experimental sensitivity grows. Implications for science and society. If a shadow universe intersects ours, measurable anomalies could appear in precision experiments, especially in systems where quantum effects are tuned to extreme sensitivity. Detectors might register signals that resist conventional explanations. Astrophysical surveys could notice subtle deviations in observations of distant objects that standard models struggle to fit. Laboratories would test these hints across independent setups. The signatures could include rare decays, energy transfers, or environmental effects that mimic known forces but cannot be traced to them. Science policy would pivot toward flexibility and risk tolerance. Funding structures would support long-term, cross-disciplinary projects that might redefine experimental norms. New instrumentation would be developed for cross-domain sensing. Collaborations would pool theoretical physicists, data scientists, philosophers of science, and engineers to interpret ambiguous data without overclaiming. Reproducibility would remain the gold standard, but the path to it could be more circuitous. Societal trust hinges on credible communication of results. Governments would craft governance frameworks for dual-use risk, data sovereignty, and international sharing of cross-domain findings. Public literacy programs would explain what cross-universe evidence means without sensationalism. Economic ecosystems could shift as new materials, sensors, and computing paradigms emerge from insights gleaned at the boundary. Privacy concerns would focus on how unexpected data could reveal sensitive information. A hypothetical sensor network could leverage cross-domain signals to enhance imaging techniques and materials discovery. There would be ethical debates about tests near boundary conditions. Intellectual property questions would surface as researchers balance open data with incentives to publish and patent breakthroughs. Public engagement would emphasize transparent risk assessment and credible limits. To sum it up, today we explored the shadow universe, a hypothetical world that intersects ours in subtle, unseen ways. We looked at what overlap could mean: faint physical signals that hint at a second realm, mirrored phenomena that challenge our usual notions of space and time, and how observers might influence what we notice. We also touched on the implications for science, technology, and imagination, and kept a steady eye on evidence as the compass for exploration. If you found yourself seeing the world through a different lens, you're not alone. Maybe you felt the pull of parallel possibilities or remembered a coincidence that felt bigger than chance. First, I'd love to hear which idea sparked your imagination the most and what question you'd want us to tackle next. If you enjoyed this dive into the unknown, consider subscribing and turning on notifications so you don't miss future explorations. A like or a comment helps the conversation grow and tells me what to explore with you next. Next time, we'll push further into the shadow universe with concrete thought experiments, potential tests, and fresh perspectives from scientists and philosophers. We'll sketch a framework for how researchers might search for traces of overlap and imagine storytelling angles that bring this idea to life.